about the product rule and the sum rule, which are two elementary rules for counting. I'd like to discuss one more idea. It doesn't have any special name, but it's very useful. So I'll introduce it in the following example. So let's consider the following problem. A file name in a certain computer system is a string consisting of 3 symbols. And then the first must be a letter, well, lowercase letter. The first symbol is a lowercase letter, while the second and the third can be either a digit or a lowercase letter. So the second and the third symbol are either a digit or a lowercase letter. There is one more additional condition. At least 1 0 must be present in the name. At least 1 0 must be present. So count all possible file names in this system. So I'll solve it in 2 different ways. My first solution is just straightforwardly analyzes what are the possible patterns, and then for each pattern we'll count using the product and the sum rules. So we have 3 symbols. The first is always a letter, second and third either a letter or a digit, and then there's an additional condition that at least 1 0 must be present. That means that either you have exactly 1 0 and can appear either in the second or in the third position, or you have 2 zeros, and then they must occupy the second and the third, right? Because the first one must always be a letter. So we observe that we have 3 distinct patterns. We have 3 distinct patterns. So we can have a letter in the first position, followed by a 0, and followed by something which I'll denote as a star, where star will be meaning letter or digit which is not 0. Or it can be letter, star, 0, or letter, 0, 0. So let's write this down, where star is a letter or a digit which is not 0. Right? And these are 3 distinct cases, so we will use the sum rule. Right? We'll separately count all the file words of the first type, then separately of the second type and of the third type, and then we'll add up those numbers. So here, for each position, we'll have distinct choices, so we'll multiply them through. So we have 26 letters, right? The second position is fixed for the first type, it's 0, and then we have 9 possible digits from 1 through 9, or 26 letters to fill the star. So that's 26 plus 9, that's 35. Right, so we have 35 choices for the star here, and we multiply them through to get the total number of file names of this type. Similarly, for the second type, we also have 26 times 35, right? 35 now refers to the second position choices. And finally, for the third type, there are 26 of them, which correspond to the choices of the first letter. And the final answer is adding them up. So 26 times 35 plus 26 times 35 plus 26, which is the same as 26, which I can pull out times 71, and that gives 1,846 different file names. Okay, so that's a straightforward application of the sum and product rule. There's a different way to solve this problem. Namely, we can treat the last condition separately, which requires that at least one zero must be present. We can first count all the complementary conditions, namely those in which 0 does not appear at all. And that's very easy to count. Just remove one digit from 10 digits, right? And you have all the possible choices. And then we'll subtract that from the total number of possible configurations. Okay? So we count first the complementary configurations. Those that do not contain a 0 digit. So they will look like letter and then followed by star star. All right, star stands for anything letter or digit which is not 0, and then this gives us 26 times 35 times 35 different file names. And then, well, we subtract that from the number of all file names with no condition on the zeros at all. So this we subtract from the number of file names with no restrictions on the number of zeros. And it's easy to calculate, so we'll have letter 26 followed by 36 times 36 times 36, right? Because 36 is 10 digits plus 26 letters. So from this we subtract 26 times 35 times 35, right? The complementary configurations. We just remove those which are forbidden, those with no zeros at all. And that gives us explicitly 33,696 minus 31,850, which equals the same number, 1,846. So this solution, the second solution, is slightly shorter here, but it can, in other problems, it can be considerably shorter than direct counting. So the take-home message from this example is that whenever you're facing conditions of the type at least something must be present, right? At least one element from a certain set must be element. Maybe advantage is to calculate separately the complementary configurations in which none of those elements is present, and then subtract from the total configuration. I'm going to do one more example on this trick. But any questions about this example before I move on? Okay. Then another example. Right, and again, certain computer system, a valid password consists of exactly 4 characters. Valid password has 4 symbols or characters. The first character must be a letter, and the other 3 a letter or a digit. The first character is a letter, and the other 3 are either letters we always consider lowercase for simplicity. Either a letter or a digit. And the condition now is that at least one digit must be present. And let's just add all letters are lowercase. Okay. How many different passwords are in this system? All right, so I will use this idea of counting complementary configurations straight away. So it's very easy to formulate which ones are complementary, those with no digits. Right? So complementary no digits. So in each of the 4 positions, we must have a letter. So we have 26 choices. So this gives us 26, 26 times 26 times 26, right, for each of the 4 positions. And this should be subtracted from all the valid passwords with no restrictions on the number of digits which can appear. So the desired number of passwords is then, so if I don't have any restrictions on the digits, the first symbol must be a letter, so I have 26 choices. The second is either a letter or one of the 10 digits, so I have 36 choices for the second one. Similarly, 36 for the third, and 36 for the fourth. And from this we subtract the complementary configurations, 26 times 26 times 26 times 26. And if you use a calculator, that gives you the answer of 756,080. So it's a rather compact solution using this idea. If you were to do it similarly to the previous problem in the direct approach, then you would have to look at all possible patterns, and then, so this is the solution finished. I'm just commenting on the direct approach. I'm not going to do it in full detail, just to give you a flavor how it would look like. So I would look at all possible patterns. It would look like a letter, and then I can have exactly 1 digit, or exactly 2 digits, or exactly 3 digits in the remaining 3 positions. So exactly 1 digit can appear in any of the 3 different positions, like this, like that. Sorry, exactly 2 digits first. Sorry, or like this. Exactly 1 digit. It can look like this when it appears in the second position, or in the third position, or in the fourth position, or exactly 3 digits, L, D, D, D. And so you see I have 7 different patterns. For each one, I have to count all possibilities, and at the end of the day, add them up. So you can see that this solution will be a lot longer. Okay? Any questions on this idea, this method? It doesn't have a name, it's just a simple trick, simple observation. Anything about the numbers here? Can everybody see where they came from? Because direct approach means that I'm counting all patterns in which at least 1 digit is present. 3 stars would mean that's what I did. That's what I did here. This is well, no, not even that. No. So this was, yeah. Sorry, it's confusing. So a star should be a letter. So we have only letters with digits. I'm sorry. I got confused myself, and possibly confused you as well. Because we had stars in the previous problem where just we cared about zeros. Here we care about the digits. So they're only letters or digits, L or D. All right? So these are all the patterns. Please correct this. Okay. So L stands for letter, D for digit. So what is missing here is 4 L's, and that was exactly the complementary configurations which we did count in the first method. Any other questions? Yes?
So for this one, you can also condense it, right? Because this would be full digit.
Yeah. Yeah, so you're right. So the first 3, there would be the same numbers of them.
Yeah,
So I can slightly improve on this. Count 1 and then multiply by 3, because these 3 will be the same, and those 3 will be the same, but still it looks longer. Yeah, certainly, it's still doable. I mean, if I had 10 characters, then it would be really miserable doing it in the direct approach. And it would be still 2 lines in this complementary method. All right, let's move on. So the next thing I'm going to consider are permutations and combinations. And so I'll start with definition of permutations. A permutation is any ordered selection of k distinct objects from a given set of n objects. Is any ordered selection of k distinct objects from a given set of n objects. Here's an example. So let's consider a set which contains 4 elements, 2 letters A, B, and 2 digits 1 and 3. Then the lists 1, 3, B, and A, 1, 3 are permutations of the 4 given elements taken 3 at a time. Are examples of permutations of the 4 given elements taken 3 at a time. Well, the keywords in the definition are ordered. So the order in which we arrange our selection matters, and also that the object must be distinct. No repetitions are allowed. So ordered means that, say, 1, 3B and B, 3, 1, although these lists contain the same elements, because the order is different, these are different permutations. Are different. And distinct means that no repetitions are allowed. For example, if I have a list in which I have a repetition, like 1, B1, this is not a permutation. Right, because one object appears twice. And I can say right away that in combinatorics, there are 4 different types of selections which arise. So you can change one condition ordered to unordered, and the second condition you can also either add, you can have it distinct, or allow repetitions. So as a result, it's also interesting to count unordered selections of distinct objects. So those we will do later today. Those are combinations. And it's also interesting to consider ordered selections with repetitions allowed. And those are very simple to count. Those are like strings of symbols. We're never worried about repeating symbols, and the order did matter, so it's just a straightforward case of the product rule. It doesn't have any special name. While the unordered selections with repetitions allowed, so those are also interesting, but they have some sort of complicated formula for counting them, so we're not going to consider those in this course. But just for you to know that it's a known instance, and you know how to count those objects as well. Right? So let's now look at a concrete example in which permutations arise in some other context, in the context of counting. In how many ways a committee with 10 members can select a chairperson, a treasurer, and an administrator among themselves? So here's a concrete question. In how many different ways can a committee of 10 people select between themselves a chairperson, a treasurer, and an administrator? Okay, so the task is to select 3 people from the set of 10. Right? First question, are repetitions allowed? Well, from the context it's clear not, because you don't want the same person to be simultaneously chairperson and administrator. So it's clear from the context that 3 different people are required. What about the order? Do we see any sign of the order here? Well, they're all meant to be chosen for different posts. So if you choose any 3 people and then you reshuffle the posts, it's a different selection. And so the order should matter. You can think about it in a more organized way. Think that, well, first I'm going to select a chairperson. So that will be the first person in my selection, or the first element in my permutation. Then I'm going to select the treasurer, and thirdly, I'll select the administrator. Right? So clearly, in each order, they will play different roles, so the order is important. So we are after permutations, so this gives a permutation of 3 people out of 10. Right, so we want to count all permutations of containing 3 elements from a given set of 10. So how can we do it? Well, we can use this order in which we will be choosing them. So first, I'm choosing a chairperson, and anybody can be a chairperson, so I have 10 choices for the chairperson. But once that person is selected, right, I cannot consider this person for the other 2 posts. So for the second post, I have only 9 candidates now. So once this post is filled, I have 9 choices for the post of treasurer. And once I've chosen my chairperson and my treasurer, I have only 8 people left, so I have only 8 choices for the administrator post. Okay? And we multiply these choices because we use essentially modified product rule here. So that's the answer for this problem, 720. This is the number of ways to choose these to fill in these 3 posts. And this simple idea of taking the choices for the first element in the permutation, and for the second, the third, and so on, can be generalized. So we will formulate this general rule as a theorem that will say that the number of ordered selections of k distinct objects out of n objects, that is permutations, is given by this formula. It's n times n minus 1 times n minus 2 dot, and I'm selecting k objects, so my choices for the last object is n minus k plus 1. And this product can be written more succinctly as a ratio of factorials. So it's n factorial over n minus k factorial. Let me explain why this is true. So the right-hand side is n squared over n minus k, sorry, not squared, n factorial over n minus k factorial. And we can write the numerator as a product, 1 times 2 times 3 times dot dot dot, and somewhere here before the final factor of n, there will be n minus k, and then followed by n minus k plus 1, n minus k plus 2, and so on, up to n minus k plus k, which is n. Right? While in the denominator, I'll have a product 1 times 2 times 3 times dot dot dot. The last one will be n minus k. So I can see that I can cancel the first n minus k factors in the numerator with the corresponding factors in the denominator. So 1, 1, 2, 2, 3, 3, n minus k, and what will remain is the same product written on the left-hand side of this formula. I'll box it. That's what we're discussing. It's just the factor, because in the first formula I have n first and then smaller numbers, while in this formula I have n minus k plus 1 first and then larger numbers up to n. But those are all the same factors. Okay, so it's just another way to write more compactly this product in terms of factorials. And the proof is essentially, a repetition of the reasoning I used in the previous example with the committee, right? So when we need to pick k distinct objects, then I can start picking them one after another, filling in positions in my permutation. So I will have n different objects to choose from to fill in the first position. Once that position is filled, that I cannot no longer pick that object again. I have n minus 1 choices for the second position, and n minus 2 for the third, and so on. And I multiply through these choices. Essentially, this is the product rule. Okay? Right. Here's an example of applying that formula. A traveling salesman wants to visit 50 state capitals in the US, each of them once. Salesman wants to visit 50 state capitals, each of them precisely once. How many different itineraries the salesman can have? Well, so what is an itinerary? It's a list of cities. This city is visited first, then another city visited second, third city third, and so on. And well, we can, since he wants to visit each city precisely once, in this list there won't be any repetitions. And the order matters, because we consider it to be a different travel itinerary if you know, the cities are visited in a different order. You know, flights will be different, and so on. So what we are dealing with is permutations. And so we have 50 state capitals, and since each of them has to be visited, we're also picking 50 elements. So we have a permutation of 50 cities out of 50. And so we can use this boxed formula to get the answer. And on the left-hand side, we'll have 50 times 49 times 48, and so on, with the last one being just 1, because it will be 50 minus 50, right? Or, equivalently, we can use the formula on the right-hand side and wrap up this product into 50 factorials. So the answer is 50 factorial. And we will talk about how large factorials are more later in this course, when we'll be talking about algorithms and graph theory. But I want to mention right away that this is actually an enormously large number. So it's approximately 3 times 10 to the power 64. So if you are to write out this number in terms of digits, you'll have 64 digits. It will be huge. Probably will go across, you know, all 3 sections of this whiteboard. But I'm not going to do it. Any questions on this problem? Do you folks see the 50 factorial as the answer? Yes? Oh, 0 factorial, that's right. Good question. If I literally just use that formula, I get 50 factorial divided by 0 factorial. And it's not clear what 0 factorial is, but the convention is it's set to be equal to 1. So by convention, 0 factorial is just equal to 1. And but if you just look at the left-hand side, you clearly see that makes sense, because you get the product from 50 to 1, which is exactly 50 factorial. Right, so it must be true. So indeed, just to remind you, 0 factorial is 1, 1 factorial is also 1. But that 1 factorial is clear, right? It's just 1 times nothing by itself. But 0 factorial is just postulated to be 1. Okay, good. Thank you. Well, we can also generalize this result, right, by looking in general case. So when we pick n objects out of n, right, when we look at permutation of n objects out of n, all objects must be present, so they only differ in the way I order them. And it's clearly, this formula can be used again, and in this case, in the case instead of 50 we have n, we get n factorial. So n factorial gives you the number of different ways to order n objects. Okay, so just a note. This solution can be generalized to the following fact. The number of different ways to order an object is n factorial. Okay, I'm going to use it soon, this general fact. But before, let me define combinations. So a combination is any unordered selection of k distinct objects from a given set of n objects. Combination is any unordered selection of k distinct objects out of a given set of n objects. Well, combinations are essentially subsets, right? You can say, in other words, it's a combination is a subset of some k elements which must be fixed out of a set of n elements. Right? Because we know in sets the order doesn't matter, right? Just a collection of objects, and repetitions are not allowed. So it's exactly what we're dealing with when we define a combination. So you can think of it as a subset. And my previous boxed formula can be used to derive the number of different combinations. So I'll formulate this as another theorem. The number of unordered selections without repetitions of k objects out of n, that is combinations, the number of combinations is given by the following formula. So it's the same as the binomial coefficient, if you know what it is. If not, I will remind you. But binomial coefficients are denoted like this. You put these two integers, the larger one on top, the smaller one below, and it reads like k out of n, binomial coefficient. And it's given by the following formula. It's n factorial divided by n minus k factorial times k factorial. I'm going to derive this formula now using the formula for the permutations. Then I'll explain what it has to do with binomial coefficients. Okay, so how can we argue here? Well, let's go back to counting permutations. So we can think of having a permutation as a two-stage process. You can think that, oh, I have to select my objects first, k objects, and then I have to pick an order. So when I select my objects, it's like selecting a combination, just selecting a subset. And then separately, I order them in some way, right? So the number of ordered selections or permutations must equal the number of combinations times the number of different orders, because you, in this two-stage process, you do each thing independently, right? So you have some choices for selecting objects and separately choices for ordering them. So when I multiply them through, I have all ways to select ordered objects. So this number of ordered selections equals to the number of k elements. Sorry, let's just add of k elements of objects equals to the number of unordered selections of k objects times the number of ways, so times the number of ways to order k objects. Okay, well, it's sort of like a formula where I write the ingredients in words. Might want also to put them into brackets, look nicer. So what does this give us? Well, we know the answer for the left-hand side, because it's in the boxed formula. So this gives us n factorial divided over n minus k factorial. And that should equal the number of unordered selections of k objects without repetition, which is the number of combinations. Let's just use the binomial symbol as a symbol which gives us this number. Let's pretend we don't know it yet. And times the number of ways to order k objects. We have figured that out in the previous comment, right? It's k factorial. So this just follows from the boxed formula, right, which we proved. So what remains is to divide both sides by k factorial. Both sides by k factorial. We get this number of combinations, k out of n, equals n factorial divided by n minus k factorial, and k factorial in the denominator. Okay. So that's how you derive it. But it appears these binomial coefficients, right? They are numbers, and incidentally, you know, notice that these numbers must be an integer, right? Because we're counting certain processes, so it must be an integer. And it's a really non-trivial fact that the numerator will be always divisible by the denominator. When you look at this formula, which is written in terms of a fraction, right? It's not immediately obvious that it will be an integer. What if it will be a fraction like 1/2 or 3/5? But it never happens, right? Somehow there's some special property of the factorials which ensures that the numerator will be always divisible by the denominator, so it's an integer. And these integers, they appear in the Newton's binomial formula. So they also appear in Newton's binomial formula. About which I'll talk tomorrow.